Welcome. This question says a 5 Tesla magnetic field is directed along the positive x-axis. The 7-loop coil carries a current of 4 amp and has an area vector of 2I plus 3J plus 1K square meter. And then there's two bits, and the first bit is what is the loop dipole moment for this system. So let's first of all visualize, and we have a 5 Tesla field which is pointing along the positive x-axis. So this would be plus 5I, because it's got 5 units in the x-axis, and plus 0J because there's nothing in the y-axis, plus 0K because there's nothing in the z-axis. And that's going to be Teslas. And the next thing we need to do is we need to look at our area vector. And our area vector is in that direction. So let's visualize that. Not trying to be realistic here, I'm just trying to do another vector arrow, so I see that they're not any special relationship with each other. They're not in line, they're not perpendicular. I'm just trying to represent another vector. And then what we have is we have a coil, and the coil is perpendicular to this area vector arrow, so I'm going to imagine it like that going. It turns out it is a coil, so I'm going to draw it with a couple of curls on it. And our current, which is flowing around the coil, is 4 amps. And we've got to be careful here about the direction the current flows. And the way you do it is you kind of make your hand into a thumbs up sign, and you use your fingers to show the direction of the current around the coil, and your thumb points in the direction of the area vector. It's the right hand corkscrew rule. And if I have my fingers pointing with that tendency, my thumb points up and to the right. So the other way to look at it is, if when you look at the coil or the loop, if the current is flowing counterclockwise, then the area vector is coming towards you, and if the current is flowing clockwise around the loop, then the area vector for the loop is pointing away from you. Either way, just practice it and learn it. And we know that my current is equal to 4 amps. And then the other thing we've got in here is actually the number of windings or turns or loops in a coil. We call it N, and N in this case is equal to 7 loops. So the current goes around once. In the first loop it goes around a second time, in the second loop it goes around a third time, in the third loop goes around a fourth time, in the fourth loop, and so on. And I don't know if it's intuitively obvious to you, but it just seems to me that if you got a certain torque because of the first loop, you'll get that same amount of torque added for the second loop, and you'll get that same amount of torque added for the third loop. So we need to add in the number of loops when we're doing the coil. If we're talking about a particular loop, we can just look at the loop. But if we're talking about the full coil, we need to take into account the number of loops. Okay, so this question asks us for what is the loop dipole moment? Okay, the dipole moment. So basically what happens is that, so we learned that torque is equal to I, A cross B. And basically what happened is people, I suppose in a way, this is not strictly true, but I suppose in a way they got sick of talking about IA, and they decided to link that together and call that the dipole moment, and they gave it the mu symbol. And that's it, basically. So we go, oh, well, then torque is equal to dipole moment cross B. For my own taste, it's like it's adding vocabulary, it's adding an extra equation, not to improve my power particularly. It doesn't make me more powerful. It just makes it so that I can talk more conveniently about something. It's the kind of thing that if you did this for a living every day, if you're like an electrical engineer, you'd fall into the habit of, you know, giving things shortened names. You say, oh, that's just so and so. So I think that's where it comes from. Maybe it's got some deeper meaning, but I don't know it. And there's the dipole moment for a loop, and then if we have a coil of them, we can have Ni A cross B. Oh, sorry, if we have a coil of them, it would be Ni A. So if we look at the question in hand, what we've got is we want to do the dipole moment for the loop, and it's going to be IA, which would be 7, will be 4, it's because the I is 4 times A, which would be 4 times 2I plus 3J plus 1K. And that would give us 8I plus 12J plus 4K. And the units, of course, would be, well, meters squared times amps. And there we have that. That's for one of them, meters squared times amps, that's there. And then if I have my coil dipole moment, so I have mu coil, which equals, and it's going to be N I A, which would be, it's going to be 7 times 4 times 2I plus 3J plus 1K square meters. Let's forget about that. We'll do that afterwards. Do all our units at the end. So then I go mu coil is going to equal, 7 times 4 is 28. 28 times 2 is 56I. And then let's have a look. 3 times 28 is 60, and 24, 84. J. And then we have 1 times 28, 28K. And our units are going to be, well, the number of turns has no units. The current is in amps, and my area is in meters squared. So there's my units for that. And as I say, so you could, rather than saying, this is a bit of an aside, so let me say, rather than saying that my torque is equal to N I A cross B, I suppose I could learn that my torque is equal to my dipole moment cross with B. And that's perfectly fine. My only issue about it then is that you have to be able to unravel what the dipole moment is every time you want to do a simpler question. So I guess do you learn it that way, or do you learn it that way? And I tend to learn things in progression. But you'll hear the dipole moment talked about all the time. So there we have it.